So let's continue here with the section of 4.2. And let's do a couple of examples that involve this natural log. Let's do once again a bit of more algebra review. And let's use the properties of the log here to rewrite an expression as a single natural log to simplify a natural log expression. All right, like suppose with part A here. Suppose here we want to rewrite the following expression of f of x, where f of x equals, say, the natural log of 9x minus the natural log of 9. Okay, so we want to use the properties here that we have above to rewrite this as one single natural log expression. Okay, well, as long as the base of our logs are the same, we can combine them together as one single log term. But we got to be careful in knowing which property to use depending on how the expression is formatted. Now here we have two natural log functions, two log functions of base e being subtracted. What can we do when we're subtracting by the same base of a log? How can we write this as one single expression? By using property number 6 here. If we're taking the natural log of some number minus the natural log of another number, then that would be equivalent to the natural log of this first term divided by the second number. So this will be equal to the natural log of 9x divided by 9. And what happens here? The 9's wind up canceling out, leaving us with just natural log of x. So natural log of 9x minus natural log of 9 is just simply natural log of x. Okay. What if we have, say, for part B? I'm just going to write this one out. Double check zoom. And for part B, we have, say, the natural log of x to the third minus the natural log of x to the 7th as the expression we want to simplify. Well, again, here we're subtracting two terms by the same natural log base, so we can rewrite this as division again. So this becomes a natural log of x to the third over x to the 7th, and then using the properties of exponents here, and this fraction that we have on the inside, oops, let me pick a different color. And the fraction that we have on the inside, we're dividing by the same base of x here, x to the third minus divided by x to the 7. What are we doing the exponents? We divide by the same base, subtract the exponents. So 3 minus 7. We essentially cancel this one out and makes this a 4. So here we're going to have the natural log of 1 over x to the 4th. Okay, yeah. We subtracted the exponents. So x to the third minus x to the 7th gives us 1 over x to the 4th. But as we saw earlier, 1 over n, the natural log of 1 over n is equivalent to negative natural log of that denominator. So this will be equivalent to negative natural log of x to the 4th power. And if we want, we can also rewrite this. Since we have a number being raised to a power, that regards that in that case that pertains to property 8. A number raised to a power, what do we do with that power? Bring it to the front. So this will equal negative 4 times natural log of x. If we want to rewrite this as simple as we can. Oops, keep putting in parentheses. So negative 4 natural log of x. Or we have another method. We have another approach we can find this problem. Again, here we have the natural log of x to the third minus the natural log of x to the 7th. And what we can do first here is use property 8. Because notice in these two terms, we have a number represented by x being raised to a power and to the p. In this case, x to the third and x to the 7th. So what do we do with those powers? Bring them down. So this would be 3 times the natural log of x minus 7 times the natural log of x. And then combining like terms by adding the coefficients. 3 minus 7, well, that gives us negative 4 ln of x, the same exact thing. Okay, one more here, part C. So for part C, we want to take the natural log of e raised to the 5x minus 2x minus natural log of 1. Okay, so let's look at that first term. Here we have the ln of e raised to some expression here. Again, our base e of e raised to the some expression. What do we do when we have the natural log of e raised to some expression? Well, essentially the natural log and the e will cancel out, leaving us with just that exponent. So this would be, so these two will cancel out, leaving us with just 5x. Where'd it go? I was going to use it right here. 5x. 5x minus 2x minus, what's the natural log of 1? Recall first property that we stated, natural log of 1 is just 0. So minus 0, combining like terms, this expression here of natural log is just going to equal 3x. So natural log of e to the 5x minus 2x minus ln of 1 is just a simple single term, just 3 times x. And so this more complicated expression is just 3 times x. Okay. So again, when a question says simplify, that means to rewrite your log expression as one single natural log term, if possible. It could be multiple terms, like I say 3x and ln, but any ln has to be written as one single term. Now, the question might also ask you to expand that. That would just be doing the opposite. That's just be using the properties to expand those expressions all the way out. But now, let's look at some applications of natural log. Okay. Suppose for this example, suppose an investment is made at a 10% interest rate that is compounded semi-annually. Semi-annually. And suppose for this problem, we want to figure out how long will it take for this investment to double. Okay, so how long would it take for this investment to double? Let's highlight some key items here. So here we have an interest rate of 10% that's being compounded semi-annually. Okay, what does semi-annually mean? Twice every year. So if we're compounding and invest an interest rate a certain amount of times per year, referring back to section 4.1, we're dealing with the compound interest formula of P times parentheses 1 plus R over M to the N times T. Right? If we're compounding interest rate n many times per year, then we use the compound interest formula. And for this formula, we have to know P, R, M, and T. But let's see what's given to us in this problem. All we know in this problem is how many times we can compound it per year and the interest rate. Notice that we don't know the initial investment. We don't know P. P is unknown. But we do know that our interest rate is 0.10, and we're going to compound this twice. And in this case, we want to solve for how long it will take for this investment to double, meaning we want to solve for T. Okay, if we want to figure out how long it will take to reach a certain amount, then that means we're solving for T. Okay, well, let's set up our equation for now. So again, since we compounded this a certain amount of times per year, that means we're using the formula of A equals P times 1 plus R over M to the M times T. Okay, but we don't know what P is. And what do we know about this initial investment that we made? We wanted to do what? We want that investment to double. Okay, we want to figure out how long it would take P to double. Let me make that note here. Okay. So how long until P doubles? In other words, how long until initial investment, which is twice the initial value represented by P. Okay. This part here, that 2 times P, again, we don't know how much exactly we initially invested or borrowed, but we want it to double its original amount, meaning we want our future value of A to equal twice the initial investment. So 2P, that's going to be our value of A. So on the left-hand side, we're going to have 2P equal P times 1 plus R, where R was 0.10, divided by M, which was 2, raised to the 2 times T. Okay? And again, we don't know exactly how much we initially invested, but is it going to matter? No, it's not going to matter here. The reason why is because to solve for T, the first thing we want to do is get rid of this coefficient all the way to the front. And how do we get rid of that? By dividing both sides by that coefficient. So dividing both sides by P cancels out that P here on the right side, and also cancels out the P on the left-hand side. So we're just left with 2 equals 1 plus 0.10 divided by 2. All right, 1 plus 0.10 over 2, that gives us 1 plus, actually do it all at once. So 1 plus 0.10 divided by 2, half of 0.10 is 0.05. 1 plus 0.05 gives us 1.05. Raised to the 2, T. Let me make some space here because we're going to do something else. So T equals 1.05 raised to the 2, T. Okay, so notice that the p-value didn't actually matter because it just winds up canceling out in this equation that we're solving for. Now the problem, then again, we're trying to solve for T. The problem with that is that T is in the exponent of the right side of this equation. So what can we do if we want to bring this exponent that involves T? What can we do if we want to bring this exponent down? This is where the properties of the natural log come into play. Recall from the properties here. If we take the natural log of some number raised to some exponent, we can bring down that exponent, be equivalent to that exponent times the natural log of our expression. So what we can do here, if we want to bring that 2t down, is we're going to take the natural log of both sides of this equation. Again, when you do one side, you have to do the other. So we're going to take the natural log of 2, and then the natural log of 1.05 raised to the 2t. And the reason why we do this is because it's going to allow us on the right-hand side here, this is going to allow us to bring this 2t to the front. So we're going to have 2t times natural log of 1.05. Okay. And so on the right-hand side, we have 2 times t times the natural log 1.05. We're trying to solve for t. So now let's divide everything that's being multiplied by our variable of t. So we're going to divide both sides of our equation by 2 times the natural log of 1.05. So dividing everything by the factors multiplying t. Okay, so here the 2's cancel out, the natural log cancels out, and we're left with that t is going to equal the natural log of 2 divided by 2 times the natural log of 1.05. Okay, and let's approximate this. Oops, I didn't say how many years, how much to round, so let's use 4 decimals for rounding this. All right, so to solve for this, let's go to our calculators. Oops, that's a zoom. And let's take the natural log of 2, which is our numerator, and divide this by, and let's use some parentheses here. Let's utilize some parentheses. So left parentheses, 2 times the natural log of 1.05, close parentheses, or two close parentheses, I should say, to give us approximately 7.1033. So 7.1033. Okay. When doing this in a calculator for your denominator especially, utilize some parentheses. So that gives us approximately about 7.1033 years for this investment of P to double its original amount. So about 7 1/10 of a year for this investment to double. Okay. Now, suppose for this problem, I should have called this part A. Let me call this one part A. Oh, now remove some stuff here. That's kind of annoying. There we go. That's what I had it highlighted. Oh, what happened here though? Ay. Okay, hold on. Gotta do some stuff here. Okay. And this was A. All right. Now, suppose for part B. Suppose for the same problem, we want to figure out how long it's going to take for this investment, for this initial investment, to increase by 60%. All right, so in part A, we figured out how long it's going to take to double. But suppose we want to figure out how long it's going to take for this investment of P here to increase by 60%. Again, we don't know exactly what P is. Our interest rate is still 10%, 0.10. M is still 2. But in this, and we still want to figure out the number of years it's going to take. But here we want this investment of P to increase by 60%. We want P to increase by its initial amount by 60%. Well, how do we do this? Well, this means that we want the future amount to be equal to the initial investment plus 60% of its initial worth. Meaning we're going to take A instead of equal to P times instead of equal to P plus 0.60 times P, which gives us 1.60 P. Right? Combining like terms, adding the coefficients. 1 plus 0.60 gives us 1.60. Okay, so the future amount should be worth 1.6, the initial investment. All right, so once again, we set up our equation here where we have A equals P times, parentheses, 1 plus 0.10 divided by 2 to the 2 times T, except now our value of A here is going to be 1.60 P equal to P times 1 plus, or as we already established before, 1 plus 0.10 over 2 is equal to 1.05 raised to the 2T. And pretty much follow the exact same steps. First thing first, divide both sides by P, get rid of that coefficient in the front, which just cancels out the P's on both sides, leaving us with 1.60 equal to 1.05 raised to the 2T. And then once again, we want to bring that exponent down in order to solve for T. So we got to take the natural log of both sides. Okay, so we can rewrite. So that's going to allow us to bring this exponent 2T to the front to give us a natural log of 1.60 equal to 2 times T times ln of 1.05. And once again, divide both sides by every factor multiplying T, which in this case is once again 2 times the natural log of 1.05. So 2 times the natural log of 1.05 to give us that T is going to equal here again, the 2's cancel out, the natural log cancels out, leaving us with t equals the natural log of 1.60 divided by twice the natural log of 1.05. Using our calculators, this is going to be approximately, well, let's see. So natural log 1.60 divided by parentheses twice natural log of 1.05, double right parentheses, approximately about 4.8166 years. So about 4.8166 years, rounded 4 decimals. 4.8166 years for the initial investment to increase by its initial worth by 60%. All right. So this is how we solve these type of log or these type of equations, exponential equations. To solve these exponential equations for the exponent, we use the properties of the natural log. To bring that exponent down where our unknown variable is included in order to solve for that unknown variable. Okay, so that concludes this section here. This little review of the natural log. So 4.1, we reviewed exponential functions. In this section, we reviewed the natural log function. And what we're going to do for the next section here of chapter 4 and 4.3 is go back to calculus and look at how to define the derivatives of exponential and natural log functions.